All right, this is a lesson on vectors for Physics 2, Summer School 2020. You should watch the trigonometry video before this video. So let's go ahead and get started with this. A vector gives the magnitude, that is an amount, it's a number value, and the direction of a physics quantity. Physics quantities that are vectors include force, velocity, acceleration, and momentum. Physics quantities that have magnitude only, that is a number only but not direction, those are called scalars. And examples of scalars are speed and energy. You won't need to know that for this particular lesson. The magnitude of a vector is indicated by its length compared to a reference magnitude. In the examples below, 1 inch equals 50 miles per hour. So if you have 2 inches, that would be 100 miles per hour. So I'm going to go ahead and just work through some examples, and you can work these on your own if you would like, and then watch me do them or just watch me do them. You should actually practice these. If you don't actually write these down, you won't remember it. So don't watch this like a movie. You have to actually be writing as you go along. Okay, so we're going to add two vectors. The first case is the simplest case, or one of the simplest cases, where the vectors are going in opposite directions. This could be a bus moving at a certain speed to the right, and a person who's on the bus moving backwards, walking towards the back of the bus, and therefore that person's speed would be a combination of the speed of the bus and their speed walking backwards, and that would be their overall speed. So let's measure this. And if we measure this longest line, we see it's 3 inches. So 3 inches times 50 is 150 miles per hour. And that's abbreviated as MPH. And the second vector, the one going to the left, is 1 inch. So that's 50 miles per hour. Now, one other thing you have to do is you have to realize that there's a positive and negative direction. You get to choose which way you want to be positive or negative, but generally we think of what we think of a number line in math. It moves, the positive numbers move to the right and the negative numbers move to the left. So I'm going to call this one positive 50. I'm going to call this negative 50. So if we want to add those two, we simply take this and then move this away from it. So that's going to put our resultant vector. These are called component vectors. So the two vectors that you're working from initially, or sometimes you're breaking things into components, and that's what we're going to be doing in the Coulomb's law lesson. Those are called components. It's when you take one vector and break it into two pieces, or you take the two pieces that you put together into one vector, and that one vector that results from that is called the resultant. Okay, so our resultant is going to be this minus this, and that gives you a line right here. Now the bigger of the two lines is pointing to the right, so this arrow is also going to point to the right, and it's 2 inches long. I just measured it, so it's 100 miles per hour. And it is in the positive direction, so we'll put a plus sign there. Okay, now you look at that and you say, well, you could have just done that with arithmetic. 150 minus 50 is 100 miles per hour. Where vectors become useful, though, is when the lines are not either parallel to each other or perpendicular at right angles. Then you can do this graphically. So I'm going to show you how to do this. This is not the way they do it in the video. This is a good way if all you want to know is the magnitude and direction. In the video, though, they're trying to come up with, in the lesson, the Coulomb's law lesson, they're trying to come up with the angle as well. And if you want to know the angle, you have to do a more complicated way of doing this. But I'm going to show you a way that is useful in most cases. This is called the parallelogram method. Some of you might have learned it as the tip to tail method. They're slightly different in the way you do them, but they're really exactly the same thing. They're essentially the same thing. Okay, so I'm going to measure this one, and this is a 1/2 inch. And 1 inch was 50 miles per hour, so this is 25 miles per hour. And this one up here is 2 inches, so that means it's 100 miles per hour. Now, this is an important concept to understand. I'm going to ask you a question. I'm going to skip down below here and ask you a question. Are these two vectors the same? Are they the same? They're the same length. They're going in the same direction, but they're in two different places. Are they considered the same? And the answer is right here. Yes. They have the same magnitude and direction. So the point is, you can move a vector around as long as it has the same length and is pointing in the same direction. It's considered to be the same vector. So what we're going to do back up here is we're going to take this 1/2 inch vector, and I'm going to try to do it without twisting my ruler, and that's sometimes easier said than done, but I'm going to slide that so that the tail of this vector touches the tail of that vector. So here goes. Let's see if I can do it reasonably well. I'm going to slide it like that, and it's a 1/2 inch, so I'm going to draw it right there. Okay, so this is the same vector as that. Okay, now I've placed them tail to tail. Now what I'm going to do is create a parallelogram. That's a lopsided rectangle. It has 4 sides to it, but the angles aren't nice square 90 degrees. Okay, so what I'm going to do is I'm going to take this vector, the 2-inch vector, and again, without twisting, I'm going to bring it down here. And I'm going to draw a dashed line. I'm going to draw a dashed line. Right about there. And then what I'm going to do is I'm going to take this and I'm going to slide it over, but really you can just connect the ends here like that, and I'm going to draw a dashed line there. So there I have a parallelogram. So what is the resultant vector of these 2 component vectors? It's simply a line that goes from where the 2 tails intersect over here to where those 2 dashed lines intersect on a diagonal across that parallelogram. Okay, and that's supposed to be an arrowhead, not the best. Okay, so there you go. So what's the length of that? That tells us the direction. So the length of that is about 2.25, about 2¼ inches. So a 1/4 inch is roughly 12 miles per hour. If 1 inch is 50, then 1/4 of that is about 12. So that means this is going to be going 2, which is 100, and 12 miles per hour. So you can think of this vector as being wind that's blowing against the side of the plane right up here. Again, remember, we can move this vector anywhere we want as long as it's the same direction of magnitude. So it's blowing against an airplane that's originally moving in this direction. And when it does, it blows the airplane off course by a little bit. You can see right here, it's going in this direction now. But you can see it's also speeding the airplane up. It's blowing slightly from behind, ever so slightly from behind, and that's causing the airplane to speed up. So that's what using this parallelogram method can tell you. What it can't tell you is the angle between these vectors, and that's what they want you to be able to do in the assignment, in the Ingenuity assignment. So we're going to show you a different way to do that. All right, so in this lesson, the vectors are combined by breaking them into their x and y components and then adding the components. So what we're going to do is just remember that an x-axis goes, well, y-axis goes up and down, and x-axis goes horizontally. So this is the x-axis, this is the y-axis right there. Okay. All right. So what we're going to do is, now what you have is a vector that you're going to break into its components, and that would be an x, something that's going side to side horizontally, and a y, something that's going up and down vertically. So here's what we do. I'm going to use centimeters for this. It works a little neater. They're a little more precise, and they have gradations of 10 as opposed to 16ths, which is what inches do, and that's kind of messy. Okay, so here we go. Here's my first, for the first vector, the x component, that is the horizontal one, the side-to-side one is right there, and I can measure it. It's 1.0 centimeters. And then the y component is right here, and it's also 1.0 centimeters. So this is y, and this is x. By the way, if you start here and move here and then up, that's going to be a positive x and a positive y. Okay, so it's 1 and 1, positive x, positive y. Now we do the same thing with this one. And what I'm going to do is come back to here. This is the x component. And that's pretty close to 3 centimeters. I'm going to call that 3.0. And this is the y component. Okay. and that's going to be about 0.9. It wasn't quite 1 centimeter. Now, if we start here and go to here, that means I had to go down on the y-axis, so y is going to equal negative 0.09. I had to go down. Then I go to the right. That's positive. So x is going to be positive 3.0. So now I have my x and y components of each of these vectors. So now what you can do is you can simply add them to get your resultant vector. So x is going to be 1.0 right here plus 3.0 right there. And that equals 4.0 centimeters. So I'm measuring everything now in centimeters. Y is going to be the 1.0 right here and the 0.9 here. Now, watch out. It's a positive 1.0, but it's a negative 1.9. I'll make my negative sign a little bigger there. It's negative because it's starting here, it's going down. Start from the tail and do what you need to do to get to the tip. So this is down, negative, and to the right, positive. This one was to the right, positive, and up, positive. Okay, so this one we're going to just put it 3.0. Oops, wrong. It's 1.0 up, positive, minus 0.9, and that equals 0.1. Okay? Right there. Okay, so now I have my x and my y. So what I can do is I can put my resultant vector anywhere on the page I want. Remember, you can move a vector. So I'm going to start right here. And the x is going to be 4 centimeters. So let's see, I'm starting here at 6, so that means I need to go over to 10. There's 4. And then it's up 0.1, not very much at all, just a little bitty. Right there. Okay? And so what that's going to give me is a resultant that looks like this. I'll draw that heavier. And the distance is, it's ever so slightly greater than 4. If this is 4, then this one is a hypotenuse of a triangle. It has to be longer than 4. I'm going to call it 4.05. I'm kind of making that one up and fudging a little. Centimeters. Okay, so there's the magnitude and the direction of these two vectors. And if you can see, one of them is going down, the other one's going up. The resultant is going to be kind of in the middle right there, and that's what you're seeing right there. Okay, now we're going to do two that couple. You can practice on these. And notice that I've put the tails together here, and they don't have to be. They weren't in that one up there, but we're going to do that here. So here we go. I'm going to draw an x component here, and that's 1 centimeter it looks like, and that was a y component, up and down, and then an x component here, and that's 1.0. So this is 1.0, and this is 1.0 here. Now what are you going to tell me about this? What about those? Something else I need to do. If we're starting here, the x was backwards. It went backwards. It's to the left. That makes it a negative 1.0. It's going in the negative x direction. So that's your x component. The y goes from here up to here. That's a positive. Remember, you start at the tail and you move to the tip. So to do that, I have to go this way and then up. And that equals positive 1.0. I'll go ahead and write the positive just to emphasize it. How about this one? We're going from here over to here. That's positive. And from here up to here, that's positive. So let's go ahead and do that. Okay, so I'm going to come over here, and it looks like I covered about 2.5 centimeters. A little bit farther. So this is 2.5. So this is the x for this vector, and that's positive 2.5 because I went to the right. And then I'm going to go up. So it really should be there, and that goes up 2.0. So this is the y component is positive 2.0. All right. So now what we're ready to do is add our x's. So the x, I'll do that over here, is 2.5. It doesn't matter which order you put them in. You add, they're going to all come out the same. So it's 2.5 minus 1.0 equals 1.5 centimeters for x. For y, They're both going up in the positive direction, so it's 2.0 plus 1.0, and that'll give you 3. So let's go ahead and draw the resultant vector right here, starting at the same origin as the other two had, and see how it compares. So x, we're going to go 1.5, that's 1.5 centimeters. That's going to take me, there's 1, there's 1.5 right there. And then we're going to go up 3. Okay, so I'm starting on 10 here. So I'm going to go up to 13, 2, 3 to right there. Okay, my hand's in the way, but anyway, that's where I put the dot. So again, I went over 1.5 that way, because that's what the x said I had to do, and then I went up on the y direction, positive 3. So there's my resultant vector. Now let's do a little test. Let's do the parallelogram method and see if it works. If it did, I should be able to take this, slide it over to here. Whoops, let me get it right. Take this, slide it over to here. And it may not be perfect, you know. That's because I'm not perfect. And there's that. And then I would take this, and I could slide it over to here. And again, it's not perfect. But there you go. You kind of get a parallelogram. Kind of, if you fudge it, use your imagination a little bit. Okay, but anyway, this is a more precise way to do it. So anyway, that's that. Go ahead and you try this one last one here. See if you can do this one. I'll give you 2 seconds to do it. Go. Okay, no, you can pause the video and start it up again when you're ready. Okay, so let's go ahead and do this. We're going to start from the origin. We're going to go down from the origin to get over to here. So let's see, that's going to be about there, it looks like. So that looks like about 0.8. And this one is going to take us, looks like about 1.5, 1.5. So this is x, positive 1.5, because it went from here to here. And you're starting here, you went down for this one, and that was 0.8. So that's y equals negative 0.8. To go from here down. Now we go to the right, that's positive on the x-axis, and there it is. Okay, now we're going to go from here, get centimeters over here, and I'm going to go from 3 up to, it looks like about 1, so that's 2 centimeters. And then I'm going to go from here across, and that looks like 1.5 as well. So the x for this one equals, again, we started here and we went up. So let's do the y first. The y is going to be positive, what did I say it was? 2. Positive 2. And the x is going to be 1.5. Positive 1.5. So now we're going to add these two x's. They're both 1.5. So x is going to be 1.5. That equals 3. Y is going to be, it's going to be positive 2 minus 8, 0.8. And that equals positive 1.2. And this one was positive as well. So where's the resultant going to be? Well, x, we start here at the origin. We move over 3, that's right there, 3 centimeters, that's what that's telling us. And then we go up 1.2. So I'm going to start here, and I'm going to go up. There's 1, and 0.2 is 2 more little lines right there. So my resultant is going to be right there. And there it is. And again, if we try to parallelogram it, you know, it's rough. It should work, okay? You'd have one there, and you'd have one there, and there's your parallelogram. It's lopsided. Anyway. Okay, so that's how you do these, all right? That's how you get a resultant from that. So you break this into an x and y component, you break this into an x and y component, and then you add the x components, add the y components, and that gives you your resultant vector. That's the way they're going to do it in the video. Okay? That takes care of that.